In our last probability lecture, we talked about mutually exclusive and non-mutually exclusive events and how probabilities started adding together. Let's continue looking at how probability adds together in this lecture. This brings in the fifth basic theorem of probability and how it gets applied given probability statistics. Our fifth theorem states that the sum of probabilities of all events in a situation is equal to 1. So this means given n possible events, A, B, C, up to whatever you want to n, is equal to 1. If we look at our probability space in these three circles, probability of A plus the probability of B plus the probability of C equals 1. This is stating that only events A, B, and C can occur. One thing to watch out for is events that are not mutually exclusive, so there's some overlap this time in A, B, and C. If we were to add up these probabilities, we wouldn't get 1. We would get something else. If that is the case, then you need to deal with the events that occur at the same time. So you've got the probability of A plus probability of B plus probability of C, but now you've double counted all these overlapping places right here. So you need to subtract out the probability of A and B happening at the same time, the probability of B and C happening at the same time, and the probability of A and C happening at the same time. Now, if you looked at where the mouse was moving over those non-mutually exclusive probabilities, you'll notice that we subtracted out this center space where A, B, and C overlapped too many times. So now we're missing that. There's a hole right here. We need to add it back in because we subtracted it out when we were accounting for the overlap between two of our events. Now, if our three events don't overlap together like A, B, and C do, all three at the same time, then this just equals 0. But when you have non-mutually exclusive events, you need to be very careful about where the overlap is so you don't end up with something greater than 1 when you add all of the probabilities together. Let's take a look at an example of Theorem 5. In this example, all of our events are mutually exclusive, so we don't have to worry about any overlap. We have three products that we're inspecting to determine if they're acceptable. We have probability data from previous trials, so we know that the probability of no nonconforming units in our sample of 3 is 0.99, or 99%. The probability of finding one nonconforming unit is 0.006, and the probability of finding two nonconforming units is 0.003. So we want to know the probability of finding 3 nonconforming units in our sample of 3. So we know, because we only have 3 pieces that we're looking at, we have 4 mutually exclusive outcomes in this example. We can have 0 non-conforming parts, so all 3 are fine. We can have 1 non-conforming part, we can have 2, or we can have 3 non-conforming parts, because we know that parts are either conforming or non-conforming. So when we go to our probabilities, we were given the probability of 0 non-conforming parts, the probability of 1 non-conforming part, and the probability of 2 non-conforming parts. Since we know we have mutual exclusivity in this case, we know that all 4 of our outcomes have to add up to 1. So when we plug in our values for 0, 1, and 2 non-conforming parts, we can subtract those from 1 to get the probability of 3 non-conforming parts. And when we do that, we find that the probability is 0.1%. If we did have some overlap in our outcomes, the only difference would be that we would have to subtract out that overlap to make sure that we weren't getting a number that was too small. So in this case, no overlap, so no subtraction. Theorems 1 through 5 are good when you have one selection. In the next lecture, we'll talk about what happens when you have 2 or more selections.